A very good morning to everyone who are joining my proposal defense. So my name is Joey, and joining us here in our committee members, we have Dr. Chef, Dr. Marco Waltota, Dr. Michael Humes, Dr. Yong Liu, and Dr. Liu. So the dissertation proposal title for me today, I'm going to present is a Neuro-Symbolic AI framework for the knowledge graph lifecycle. So let's talk a little bit about the motivation why we need knowledge graph in general. But taking a step back, in general, the modern AI systems, particularly like large language model, they are very capable. However, there are more models based solely on statistics and dictated by the underlying training data. So if you can look at the figure on the left, that is the BERT architecture that sparked the growth of language model. And then on the right, you have the GPT transformer architecture. So what are some of the limitations of this kind of architecture is that data inherently they lack meaning. So it shows correlation, but not causation or explicit semantics. Data lacks context. It cannot reliably disambiguate. And also data lacks provenance. For example, if you're trying to ask where does this fact come from, it is still true at this current time. So relying on data alone is not enough. The argument here is that we have to augment data with explicit verifiable knowledge. So nowadays, in most enterprise settings, we have data being stored in distributed data silos and data warehouse. This is a very standard practice because every organization have different departments, different teams, so they have their own kind of localized requirements for their data in and out. So the thing about this is that AI models doesn't have any inherent mechanism for factual updates or source attributions. They are inherently in the black box in nature and prone to hallucination. So now the research, as of right now, the current era is that everyone is jumping into the AI ship, but in the way that they want to connect all this together. That's why you have the term context engineering. So basically, what context engineering in general means is that to make all these LLM systems useful, one has to or must connect all the proper context, attributes, and also anchor them in a well-defined semantics. And one of the popular ways of doing it, or everyone is actually doing it, is with ontologies and knowledge graph. So I'll give a reason why knowledge graph is being used. So here are some examples and some of the popular use cases in generative AI with the using knowledge graph. So we know that modern LLMs, they are excel in learning patterns and generation tasks, but they are prone to hallucination. And these are some of the example uses of knowledge graph in Gen AI systems. So for example, knowledge graph, it's able to provide factual grounding to reduce hallucination, improve relevance and context awareness, enhance explainability, personalizations, and also domain-specific accuracy. So here are some of the questions to give you in context, what are the ones that require the use of knowledge. So for example, in the sales or business or enterprise settings, if you want to ask who are the people in my organization that has prior engagement with this buyer, and then who are all the connected contacts for buyer and sellers, these are all questions that require people information. Like you need to have the people connections and people knowledge. And then let's look at the medical device and healthcare settings. If you ask the question, does the Capnol Stream 20P support the monitoring of SpO2? And then in which component enable this capability? And if you ask to provide descriptions, all this require inherent domain-specific knowledge to be able to answer these questions. And then, of course, if you ask in the pharmaceutical domain, like identify all pharmacological substances that are explicitly linked to migraine. Again, this requires the domain knowledge of pathways, chemical substance, as well as the everything about, you have to know about the compound itself that you're trying to link. So we know that knowledge provides us with that source of knowledge, but then the process is the process of creating and managing knowledge graph is a complex process. So we know that there are many knowledge graph tools that exist out there. But they exist in silo. There are tools that are good, that are just meant for managing knowledge graph. There are tools for manipulating knowledge graph. There are tools for creating ontologies. But then there is not one end-to-end pipeline or a one tool that kind of address all the different life cycle in knowledge graph. So this prompted the need to have a neuro-symbolic approach to develop and maintain the real-world and complex knowledge graph. So here are some of the different aspects of knowledge graph that we want to deal with. So during the process of creating knowledge, it is very important to have these elements here: provenance, where are this knowledge and data coming from. dynamic. The knowledge itself has to keep up because knowledge evolves over time. The schema itself has to evolve as well. Temporal, again, knowledge gets updated every so often. We have to keep up where the time element as well. And then speed and expressiveness. Obviously, as the knowledge graph gets bigger, we want to balance the expressiveness and also the speed because we are ultimately going to use this knowledge graph for any production systems. We have to be able to balance that. And then coming down to the applications, we also want to maintain traceability. When you use knowledge graph to question answering, we need to have that kind of traceability. Where does this answer grounded from which knowledge? And then alignment, and of course, finally is the evaluation of the knowledge graph, how good it is, and how good can we use it for our downstream applications. So all these elements of constructing and managing knowledge graph will be addressed in this dissertation proposal. So now let's take a step back. So I introduced a lot of terms here: ontology, knowledge graph, and world model. So this slide here is kind of show an overview. What are the different definitions that are used in this presentation, in this dissertation? So when I mentioned ontology, basically ontology is the schema itself. Think of it as a schema. So it is a formal specification of a shared conceptualization. It sits at the abstraction level, defining all the classes, properties, and logical axioms. So think of the role of an ontology as a reasoning and for consistency checking. And also it is meant to describe semantics. Think of it as the grammar rules of a language. And for example, if you ask if X is logically valid, so this is how the schema ontology comes to play. And then after that, once we have the ontology, it provides that schema for the knowledge graph. So knowledge graph is the instance level, the instance data. So it is actually a graph structured modeling and database that store the real world nodes and relationship. So knowledge graph focuses solely on the instance data. So the role here is for retrieval and connectivity. It connects all the scattered facts into one single network. So the primary focus is on data. Think of knowledge graph as your dictionary. And then the task here is that how is X connected to Y? It's meant to enable multi-hop reasoning. Then on the right-hand side, we have the world model. So what is world model? In this case, it is an internal representation of an external environment used by an agent, AI or human, to simulate actions. So the knowledge graph if knowledge graph is the dictionary, it is providing the state space for the world model itself, because world model is being used for planning, counterfactual reasoning.
Why would this is things that are part of the world model not part of knowledge graph?
No.
In the past, we used to do that.
Yes. So knowledge graph itself is a technology that enable the world model representation. So knowledge graph is the backbone for that world model. World model again is the representation of the external environment, how we model the world. But what drives behind the modeling is the knowledge graph. And the world model here is the analogy is to do tasks like dynamics, cause and effect, the ability to write news story, for example, the ability to predict what happens if I do X. So
can we take one example in your dissertation, and any one example, let's say pharma, and or something else, and just give a very concrete example, because that will be very valuable.
Yeah. Okay. So in the world model, basically if you take the example of pharmacology or pharmaceutical, for example, we know that drug A is connected to disease A. So this connection here, and then how disease A has side effects, and then how disease has different medications. All this different world model representation, the external environment that are all being represented and driven by the knowledge graph itself. And then knowledge graph itself is being specified by the ontology. So, but the purpose of using world model typically is to simulate that environment for downstream applications, like for AI agents, to be able to carry out tasks based on that world model, based on that modeling that is being represented by the knowledge graph itself. So for the scope of this dissertation proposal, we will focus on the development and creation of the ontology and the knowledge graph, which in turn will be used to for some examples and use cases in downstream application. So here is the knowledge graph lifecycle and the research questions for each component. So when we talk about knowledge graph, when we talk about how do we develop and also maintain it, these are broadly the 4 different components that one has to go through to create a knowledge graph. So first we start with the data interoperability. Basically, we identify what are the different types of data that we have: structured, unstructured, semi-structured. How do we connect them all? So in order to connect them, we have to go through a representation layer, which again, it's to define the semantics. How do you want to represent all your data in a coherent manner? This is why we use knowledge graph in the first place, because in the representation, we focus on traceability, provenance, attributions, and also the temporal aspect. Then once you have the representation, you go to the next phase of alignment and enrichment, because now when you have different sources of data being represented, now you have to align them, because, for example, certain concepts are being expressed in different ways and different terms has to be aligned in order for your graph to be able to enable knowledge discovery, for example. And then the final one, once you have this graph, you can use it for consumption and then evaluation. And then the cycles continue, because developing and maintaining knowledge graph is not a one-off process. It's actually a cycle. Once you evaluate the knowledge graph, you kind of go back and identify what are the missing gaps, and then go through the process again, and then so on and so on. So it's a continuous knowledge updates and maintenance. So for this dissertation proposal, we look into 4 different research questions here. So the first one is on data interoperability. So the research question here is, how can an ontology be designed and used to model sequential processes, integrate fragmented data silos, and answer competency questions in enterprise settings? So this is mainly to address why do we need ontology and knowledge graph in the first place. Then the research question number 2 is, we know that knowledge evolve over time. So how can knowledge representation be designed to formally model the interplay between the data provenance and also the temporal dynamics while balancing the expressiveness and efficiency? Then moving on to research question number 3, what are the conceptualizing information that can be leveraged to align for a given pair of entities and concepts? Because ultimately we want to align multiple concepts that mean the same thing or different together to have a unified representation of the domain itself that we want to model. And then finally, research question number 4 is, how do we consume and evaluate the quality of the knowledge graph at the application level? Because once we have this knowledge graph, we want to use it, right? So in our case, for the sake of narrowing the scope of this dissertation proposal, we are using our knowledge graph specifically in augmenting the LLM context for question answering and evaluating how it can improve traceability and also reducing hallucinations in LLMs. So all these 4 components of knowledge graph lifecycle and their research questions contributes to the development of the EMPWR platform, which is a neuro-symbolic AI framework for creating and managing the knowledge graph lifecycle.
Hey, I have a question.
Yes.
On this slide, where have you captured the fact that the meanings could change over time?
Yeah.
Yeah.
So that is on research question 1 and 2. That's when once we go through the different component cycle here, and then at 4 we go back to number 1. So which means at the consumption and evaluation phase, if you're identifying some missing semantics or missing representations, then we go back to step number 1 to go through that process again, identify what are the additional data that we can use to enrich the knowledge graph. And then again, we expand on that in terms of the representation. Then of course, when we evolve our schema, we have to align them again to make sure that we add resources, add new information. Then again, we evaluate knowledge graph that is being generated, the version 2, and then cycle continues again.
Sounds like you may want to consider provenance of meaning along with provenance of other things to capture that. Yeah.
Yeah, that will be addressed in research question number 2, right, where we in the representation layer.
All right, thanks.
Okay, so moving on. So this is the proposal statement. Creating and managing knowledge graph is a complex process knowledge graph tools exist in silo, there is a need of a neuro-symbolic approach to develop and maintain the knowledge graph lifecycle. So this work introduces EMPWR, which is a framework that operationalizes a traceable and dynamic knowledge representation and alignment model for data interoperability and to augment LLM context for consumption, improving the attributions and reducing hallucination for evaluation of the knowledge graph.
I do welcome committee members to later on, give your suggestion on the statement. It could be formulated a little differently, but when it expresses what is being done, but maybe formulation may be slightly somewhat different. Thanks.
Yeah. Okay. So this will be the outline of the presentation structure. We'll start off with the foundational work that has been done so far for each component and each knowledge graph layer. And then part 2 will describe some of the ongoing work, the remaining work for this proposal. So now, addressing the research question number 1, how can ontology be designed and used to model non-sequential processes, integrate distributed data silos, and answer competency questions? So we demonstrate a use case in the enterprise setting. So in the enterprise settings, typically it involves a sales process, and a sales process involves multi-actor. We have seller and buyers of different roles, and then it involves multi-activity, where each process can be labeled differently depending on who are the actors. So we have, in a sales process, we have 5 main different stages: discovery, demo, assist, propose, and commit. So traditionally, they are being modeled linearly, but as we advance in this current generation, with the rise of so many technologies, the sales process has been all over different stages. So it's a non-sequential process. So now the challenges here is finding the right people to start or resume a sales process is challenging because of the non-sequential process of sales that we model, and then the lack of proper usage and understanding of content generated from all the data that are available. So how do we connect them all? So now let's take a detailed view on the challenges. So I want to bring your attention to the 3 C's here: the content, and also context. So in terms of content, we have data that is scattered all over different data warehouses. So if you ask a questions, who are the prospects that have prior email engagement with the users in my organization? Because we want to connect the sellers and the buyers and also the corresponding salesperson with the right requirements. These are one example that we kind of have to join a lot of different tables because that table exists in different departments. They serve different purpose. And in order to answer just not simple, but rather this specific query, you have to do a lot of joins, and it does not scale, and it gets very expensive in terms of query time. And then on the other hand, in terms of context, we have localized data models spread across different databases and data warehouses across different teams. So now this creates a data semantics and data meaning gap between the data producer and the consumer. So we don't have a globally unique organization representation. Every department uses different terminology to describe the same concept. So now that leads to the problem of context, as in we have all this information available sitting in multiple warehouses, yet we still lack the contextual information needed to answer some of the questions, like for example, finding the right people to start a sales engagement. So now, connecting all this, the goal here is to answer complex queries and use case scenarios. The end goal here is to achieve a better guided engagement between the buyer and sellers to get a positive engagement outcome. So here is the problem statement that we want to connect the content, context, as also the contact information. So now, however, the challenge here is that connecting all this require proper modeling and data mining in order to derive actionable insights. So in this paper, our contribution is defining a sales engagement graph framework. So we have 3 different phases where we capture the requirements of the domain itself, model it, and then we illustrate how we can use this to be able to answer the complex questions that are being shown in the previous slide. So the actual use case here is harvesting people information from emails. with the sales engagement graph, because in sales, ultimately we want to connect the right person with the right prospect. So it prompts us to discover who knows who information. And in order to model this kind of network, we actually develop a sales engagement graph ontology to model the relationship between the actors and the activities in a sales process. So in order to populate, so now we have the ontology. In order to populate this ontology to create the instantiated knowledge graph, we are housing the information from engagement logs and also emails. And then in terms of evaluations, this pilot knowledge graph, sales engagement graph, was able to extract 4.7 million engagement log. That we housed a 64,000 new discovered person entities that represented a 20% increase in terms of the number of people information that are just sitting in multiple warehouses. We are able to connect them all. That translates into a better coverage of all the people that are involved in the process.
So many people involved in the process?
So not many people in the process. It's we are able to connect all the fragmented people into one graph. So now when you query that graph, you can look up, for example, John Doe. You click on him. Now you're able to see who are the ones that are connected.
Connects basically connection graph.
Yes.
For
exactly.
Sales of.
Yes. It's a connection graph. So this is a snapshot of the sales engagement graph ontology, where we model the data integration and concepts and relations as the first-class citizens. You can see there's a person here, and then the messages, data sources. So now we have the graph. Now, how do we put it into action? So this phase here models the temporal evolution of knowledge. You can see that when we develop our sales knowledge graph at time step 0, it looks something like that. And then, of course, as time goes by, the knowledge graph evolves over time. So it has more actor, the buyer sellers involved, and also more activities that are being involved. So now this is a sales process view that evolves at multiple time steps. So now, how can we do one level abstraction on this graph? We can we do the multi-label sales activity. Basically, we are labeling at this stage, this graph here. This is considered a demo stage, and so on and so forth. So now at the time step 3, this graph here with all the connected actors and activities, it could mean assist, propose, or commit stage. And with all this, we are able to create the model the non-sequential processes with just this kind of sales engagement graph modeling. So now, with all this non-sequential processes being modeled, what can we do with it? What we want to do here is, first, is to find the best action path. So we want to, with this graph that we instantiated with all the data that we have, we want to calculate the impact and also predict an outcome for an action path based on the weighted transition probabilities. So for example, let's say you are in demo phase, and then you want to move on to the next phase. Well, based on this current information, contact, content, and context, what is the likelihood of one phase transitioning to another phase? This will generate a lot of insights for the sales rep. And also the next goal here is to generate turn-by-turn micro actions. For example, let's say I'm in a demo phase. What can I do next based on the past data to be able for me to advance to the next phase? Probably we want to close the deal as soon as possible. So let me put this into a use case example. So before the sales engagement graph, we have a sales rep asking the question, what should I do next to push for a positive engagement outcome or to close the deal? But now we have the 3 different C's that are being modeled: contact, content, and context, modeled by the sales engagement graph. Now we have all the information to be able to answer that. So the next best action is to schedule a meeting call between 8 to 10 in the morning with the VP of sales and present a product demo. So overall, the takeaway for this research question 1 is ontology and knowledge graph can be designed and used to model non-sequential processes, integrate data silos to answer competency questions with respect to the knowledge definition that we define. Knowledge graph defines semantics to connect the data from different sources as well. So now we know that now clearly the role of ontology and knowledge graph. Now moving on to the representation. We know that now you can use knowledge graph to answer and also address some of the questions that we want. So now, but the thing is, knowledge evolves over time. So how can knowledge representation we define to model to formally model the interplay. You want to capture the data provenance and also keep up with the temporal aspect as well, while balancing the expressiveness and efficiency. So this is a background slide. Broadly speaking, we have two different dimensions in terms of knowledge representation models. We have the RDF and also we have the property graph model. So RDF typically model a fact or a knowledge in triple form, subject, predicate, object, while property graph model the same thing, subject, predicate, object, but at each node, subject, and also the predicate node, predicate, the ages, you can assign, you can put in properties. I'll show you examples illustrating how the differences are. But for that, why people still use RDF to this day? Because there are certain advantages that are offered that are beneficial. So RDF, because it's a W3C standard, it offers a standardization and interoperability. Because once you define the schema in a R format that you can publish online, it allows the it allows formal semantics on the internet. So which means any data that is connected to this URI, they are actually unambiguous, and machine can actually read this and get to know, okay, this concept, this string here is connected to this concept, and this concept is being described formally this way. So this allow further inferencing. So for example, if you define in your ontology, a dog is a subclass of animal, and then you have an instance, Fido is a dog, then you can infer that Fido is an animal. And because of that, it allows us a lot of data integration, because every concept has its own unique identifier on the internet. However, the limitation is that it is a very basic representation, subject, predicate, object. So in order to add simple property to a relationship, for example, you want to add the provenance, metadata, or even temporal aspect, you have to verify. There's something called RDF verification. Basically, you are adding more triples to describe that relationship. And because of that, depending on how many relations you have, it could explode the number of triples, which ultimately lead to deep graph traversals in Sparkle. So on the other hand, this is a property graph model where you can see the nodes and the relations, they can have properties defined within them. So languages like Cypher, Neo4j, for example, they are designed to specifically to traverse this kind of graph structure, which is very fast. However, the limitation is there's a lag because of this modeling. They have a lack of single standard. When you subscribe to Neo4j Cypher query, for example, you are essentially being tied to the specific vendor, leading to a vendor lock-in. And then if you want to switch to a different graph database that uses a property graph modeling like AllegoGraph or Stardog, not Stardog, but other property graphs, you essentially kind of subscribe to their language and also ecosystems.
I have a silly question, I think, a really basic question. This would be in your dissertation document, would this be part of chapter 3 in your proposal? Yes. Okay, very good. But you don't have this kind of detail there clearly in a way. Right. Okay, very. Okay. Are you planning to add it? Yes. Yes. Okay.
Yeah.
The dissertation itself.
I don't know if people wanted to spend so much time at this level, so let's get the approval on the whole thing.
Sure. Thank you.
Much of this is already in the publications.
Okay.
Yeah. So here's a background. What exactly is RDF verification? So I'm going to use an example here with the singleton property model. So this model, basically, you can look at this. When we start to represent a fact in triple form, for example, in this case, we have Bob Dylan is married to Sarah. We want to model the time and also the aspect related to this relationship. So how do we do that? So in the singleton property graph modeling, we verify the predicate itself. So is married to is now a singleton property of is married to. So now this is married to relation is being verified, and now you can add more statements that describe this relationship. But then, so if you look at this kind of representation in the RDF manner, it is very similar to the property graph where you add properties at the ages itself, at the ages level. But then if you try to run a Sparkle query on this statement number 2, T2, it cannot be used to effectively traverse this model. It's because the singleton property of is married to, it's a all variable query. Basically, when we want to look for this specific statement, Bob Dylan married to Sarah, we have to start on this T2, which then prompt a full traversal on the entire is married to. How many instances? Let's say if your is married to singleton property has 1,000 instances, it has to go through all of that to find the exact one that connects this particular triple. So it's a very expensive modeling approach. So now, given we find the similarity in terms of this singleton property RDF modeling and the property graph, the research question here is that can we develop a common graph model that leverage the expressiveness of RDF and also the efficiency of a property graph? So in developing this model, we name it the property graph, and these are the 3 different requirements that we consider. First, we consider the intrinsic similarities between the singleton property RDF versus the property graph H, and then we want to resolve the performance issue with respect to all variable query pattern in the Sparkle manner, and we want to enable support of singleton properties additional metadata values. So this is how we finally came up to model. So you can see that on the top is the property graph modeling, where we have the subject and then predicate as an H and then object. We turn in this representation, we turn the predicate explicitly as a node. So now we have a subject node, relation node, and also the object node. So the motivation why we are modeling in this way, and this is the principle. So because ultimately when we model a knowledge, there's so much metadata that we want to keep up to. We want to keep up with the traceability, we want to keep up with the temporal aspect as well. But how do we model all this information at the H level? We simply could not. So by turning the relation node, relation H from H to a node, now we can add a lot of properties in this relation node itself. And then we can branch it to different W3C specification. If you want to link it to the W3C time ontology, you can just link it out, has temporality. If you want to link it to the W3C provenance, you can just link it to the traceability model, where we describe all the source information. So now the question here is, we have this representation. Now we want to balance on the speed as well, the speed of retrieval. So now the question to ask is, what do I specify on the node itself, the relation node, versus what to link out as new nodes? So to balance the trade-off, we design this approach where we keep all the commonly accessible, commonly queried metadata, like the evidence snippet. So for example, when you extract this, create this triple, the source of this triple, where is it from? It is at this sentence and this paragraph. We want to keep that in the node itself. And then what time it is being created, when is it updated, and then the assertion, is it asserted by a language model or is it asserted by a human, and what is the confidence level? So these are the commonly queried metadata. We keep it at the node level. And then if we want a more comprehensive modeling of the traceability, we will link out to a traceable node. So in this case, we are tracing it to a PDF, source PDF, which has its own properties like file size, authors, and so on and so forth, depending on how you want to model your provenance node. And then the temporal as well, the valid from, valid to. So it opens up so many possibility on how you want to model it in this way. So the premise here is an H is just a connector, but a node is an event. We need to treat facts not as simple connectors, but as auditable events. And what I mean by auditable events is, can we assert this fact is asserted by this person, this model, at this time from this source? So a standard H just couldn't hold that level of rich information. And this is the motivation of why we model in this way. So we actually ran some experiments in this modeling approach on the PubChem and also BKR. BKR is the Biomedical Knowledge Repository. and we transform the property graph modeling into this singleton property graph, where the relationship are being modeled as a node, and these are the results that we get. So the takeaway here is that we achieve decent performance in terms of the number of triples, query size, and the query execution time. So we ran a few variations of queries in terms of join, filter, all your standard ones, and every one of them are able to achieve less than one second query time. So we have speed is decent. And then the query, SPG query itself, they are Sparkle compliant. We can express it in RDF. So this approach here support the expressiveness of logic while providing an efficient implementation for graph traversing purposes. So now on the representation.
Quick question.
Yes.
You said the SPG can be used as a semantic web abstraction layer on top of graph database. What?
Yes.
So you basically have two databases.
Just one. So basically, the implementation is on property graph, but then on the property graph itself, the modeling is using SPG.
So this graph database needs to support both Sparkle query and the traditional or classic Cipher query, for example.
So the conceptual modeling here, it's deployable in both RDF triple store or property graph. Because the goal here, this modeling, we want to be domain technology agnostic. We want to be able to, you can implement this approach using any RDF store versus property graph. So it doesn't mean you're stick with one approach, stick with one, lock into one specific vendor.
Okay, so it's vendor neutral, but then when
Yes.
you say graph database, maybe you can clarify what it is. Maybe later. Yeah.
Yeah.
Yes, use Neo4j.
Yeah, in this case, for experiment purposes, we are running through Neo4j, but of course, for benchmark and for query. But of course, the modeling itself is vendor neutral. You can do it in Sparkle, RDF, if you so forth. If you want, if your domain has more compliance need that has to be conformed to W3C standards. So that's this modeling offer that kind of flexibility to be able to do that.
Okay. Yeah. Okay. Thank you.
So now we have the representation. So now let's move on to the next research question, which is the alignment problem. So what are the contextualizing information that can be leveraged to align a given pair of entities and concepts? So we will demonstrate this with a use case on the UMLS meta thesaurus, which is basically a biomedical vocabulary. So just a background of the datasets, the UMLS meta thesaurus. So this is actually a knowledge graph itself, and this knowledge graph, UMLS, is connecting all the biomedical terminologies from different sources like MASH, MEDRA, RxNorm, ICD-10, SOMACT, and so on and so forth. So this UMLS knowledge graph has more than 10 million English medical terms from 210 source vocabularies. And the way that this knowledge, this UMLS cluster together synonym terms is by manually approach. So they have human editors that manually cluster all the synonyms together, and then all these synonymous concepts, they are being assigned a concept unique identifier. So this is one example. So you can see here the picture on the right, we have Addison's disease. So Addison's disease is a preferred term, and under this term, you have all the synonyms, Addison disease from this source, MASH, and then primary hydroadrenalism from MEDRA, and so on and so forth. All these synonymous terms that are being associated with Addison disease are being labeled as C0001403, and that is the concept unique identifier for this specific concepts. But the idea here is that synonyms are being grouped together, and the approach of grouping this currently is by manual. That's why UMLS meta-thesaurus is being updated 2 times a year, every 6 months, from all these medical sources. So now, and because it has more than 10 million medical terms grouped into 3.85 million concepts, CUIs. So now is a very challenging process, and also very taxing and time-consuming to do it in a manual way. So what if a new source are being updated? How do you inject or insert that new concept to one of the concept buckets here? So we turn this into a alignment problem, where basically we want to identify the synonyms and non-synonyms among the UMS concepts. So concretely, the problem is given 2 atoms. Basically, atoms is each medical term here. Yeah, are they synonymous or not? Are they belong to the same concept unique identifier? So the goal is to learn the similarities between the atoms that are synonymous versus that are not. So here are 2 examples here. So on the left, we have lung disease and disorder. And then on the other hand, we have head disease and disorder. So you can see that these 2 concepts, 2 atoms, they are lexically very similar to each other, but they are actually not synonymous. So lung and head, they are not synonymous. But then the rest, they are lexically similar. And then on the other hand, we have the example of 2 atoms that are lexically similar. They are not at all similar, but they're synonymous. Like, for example, Addison disease and primary adrenal deficiency. So is there a way for us to develop an approach to align these 2 concepts together? So if so, what are the contextualizing information that we can use to connect and merge these 2 concepts? So let's take a concrete look. And this is our approach. We term it as the context-enriched knowledge graph. Basically, we start off with given 2 concepts, co and co. How do we disambiguate and align them, or make sure that they're actually synonymous? So now the first thing, this approach, we introduce the use of synonyms. For example, we look up the neighborhood information, the synonyms. So co is the synonyms from, is referred to, on the left one is referred to the chronic obstructive lung disease, and then on the right is referred to common cold. Is that good enough? Maybe, but let's see. So if you add on the hierarchical information, like the parent and children relationship, now it gets a lot clearer that this co has the children of pulmonary emphysema and the parent of chronic lung disorder. And then on the right-hand side, that co concept referred to a viral tract infection. So now we have
I have a question, Joey.
Yes.
Yeah. So how does this compare or can be combined with semantic embeddings and vector space approach which LLMs take?
Yeah. So this is just a representation layer. The approach will turn this into a semantics vector space to train a model to be able to do this task. I'm going to showcase that in the next following slides. Yeah. And finally, we can also add on the semantic group itself. So this code, even though in this example, they're semantic group, they are both in the disorder, but you can see that these are some of the contextualizing information that we can leverage and use to disambiguate and align similar concepts. And this conceptual approach can also be applied to any other domains where we have, as long as we get the neighborhood information, like the non-hierarchical one, like synonyms, and also their hierarchical information, like for example, their parent and children. On top of that, if you have one layer of abstraction, like their semantic group, or maybe their classes that they belong to, that also can be used. But for the case of this specific use case, UMS meta-thesaurus, these are the contextual information that we use: the source synonyms, the semantic group, and also the hierarchical relations. So all this modeling are being transformed into the knowledge graph embeddings. So this is to answer the Dr. Whipple, your question. So basically, when we start all the way from the bottom, where we have the atom, which is the term itself, co and co, left and right. So we use your traditional lexical organizer, turn it into a lexical representation, And then and also we incorporate the different level of contextual information, source synonyms, semantic group, and also source hierarchy. And then at the very end, we merge them and then add on a few dense layers and calculate the Manhattan distance between between the two concepts. Are they synonymous or not? So basically, we are calculating the similarity between 0 and 1. Given these two concepts with their respective lexical vector representation and their contextualizing vector representation, can we concretely disambiguate them? And this is the results. So this figure here is showing the best result. We use 7 different kind of knowledge graph embeddings. Let me just show back. Yeah, so we have trans E, trans R, belonging to the translational distance-based approach. And we also use semantic matching based like Dismount, Whole E, Complex, and Rescal. And also we use neural network based like COF, KB. So these are the different families that are popular knowledge graph embeddings that use the translate orders triples into their vector representation, and we test them all. And this table here shows the best performing ones, which is the complex embedding technique. So in benchmarking and testing the different the alignment contextual information, we have these 3 different objectives. So the objective number 1 is, can the contextual information that we use outperform or improve the performance of just using the lexical representation? So yes, the use of knowledge graph embeddings to add contextual information to the reference lexical representation yielded performance improvement over the baseline with no negative effect on recall. That's objective 1. Then for objective 2, does adding context type individually or collectively perform the best? So con all is contextual all. So as in we use all the context type, they perform the best with no single context type outperform the con all across all knowledge graph techniques. So the more contextualizing information you have, the better the performance. And then objective number 3 is to assess the impact of adding this contextual information on specific data sets. So because we want to disambiguate this example here, coming back to this. So we, in our generalization data sets, we have these 2 different examples here. These 2 groups, we have atoms that are lexically similar but not synonymous, and also we have lexically not similar but synonyms. So we have 2 groups here. So the objective number 3, the largest gain F1 is observed within the data set that contain the highest number of lexical similars. So which means this example here, co and co, we are able to achieve the highest F1 gain. So yeah, so that's the alignment problem. So now bringing it all together, we have the EMPWR platform. So in this, so we're gonna introduce that. So this is the EMPWR architecture. This is to address the problem of knowledge graph tools that are existing in silo. And this platform here is meant to connect them all. So this is an overview where it combines the neural approach, where we are tasking the embeddings and also machine learning and language model to be able to do the knowledge extraction from the data sets. And then on the symbolic side is, how do we connect all the extracted entities and relations to external authoritative sources, like pharma, to Mayo Clinic Drug Bank. And then I'll show a concrete example how to do that, but this is the overall. And then all the entire workflow is being captured on the CMF, which is the Common Metadata Framework developed by HP. So this is a concrete kind of walkthrough on how do we use the EMPWR platform to be able to generate a knowledge graph. So in this case, we have a QA. We have how does methotrexate treat rheumatoid arthritis. This is a very standard QA that you find in the QA data sets. So in order to answer that, this question requires additional context on what this word methotrexate means. So here, using the LLMs for the co-start problem, where we generate the seed knowledge graph. No, now we have methotrexate is the drug used to treat rheumatoid arthritis. So now how do we link it? Get more information. So here on this box here, it's to extract it with LLM. We identify the triples, relations, and entities, and then we connect each entities to their relevant drug bank ID in this case, and then we link it with their corresponding drug bank ID. Now, when you click on this link, we have all the more information about this specific compound. We have their brand names, background, associated conditions, product ingredients, and so on and so forth. So now we get more information about this specific compound. And then in order to infer the schema from this approach, tagging. So all the triples that are being extracted here are being tagged at this level. So we have drug, medical condition, treated disease. So it's kind of, this approach bootstraps the data-driven approach for able to create the ontology and the knowledge graph. Of course, the schema, once we generate it, we also align it with the external concepts like concept net and also word net. So now we have this enriched knowledge graph where we have metro tracing not only not only we have the information at the data level, we also have the knowledge at the from the different other sources. So now we have more information regarding this metro tracing to be able to effectively answer this question. So the last research question, which is the consumption evaluation, this is an ongoing work. So how do we, so now we have this knowledge graph being built. So how do we consume and evaluate the quality of the knowledge graph at the application level, specifically in augmenting the language model context, improving traceability, and reducing hallucination? So we will demonstrate that with a use case on the medical device. So in the medical device domain, the input is it's all the PDF documents, FDA 510K documents, and a 510K ontology. So given all this documents, how do we turn it into a knowledge graph? So we go through the EMPWR platform to create this knowledge graph here. So now once we have this graph, we are using it to augment the language context. So the goal here is to use this platform to integrate documents from different systems to enhance R&D. And then in turn, once we have the graph built, it is being used for LLM consumption as context for question answering. So now, this is the representation. Yeah, you probably have seen that in the earlier slides. So for example, in this is what the level of metadata that we are capturing. So for example, if we go through the documents, when we extract this triple here, Capnol stream 20 intended for CO2 indications, this triple is being modeled like this. So we have the subject and the relation node and then the object node. So on the relation node, we are capturing the evidence snippet. Where exactly is this triple being extracted from? That is being extracted from this sentence here. The Capnol stream 20 is intended for CO2 indications. When does it capture? Created at, last updated at. How does it being asserted? In this case, we are using language model. If you have humans in the loop, then we can update this as the human expert that human asserted this fact as the correct one. Then after that, we branch out to the provenance node, where this is coming from this PDF file, and then we also branch out to the temporal node, where this fact, this triple here, is valid from this time to this time. So now this specific model.
I have a quick question. That has traceability link, right? Would it make sense? At what level of granularity are you capturing? You could be at the sentence level, paragraph level, document level. What are your thoughts there?
So that we can capture both. So at the evidence snippet, we can typically what we do is we do it at the source level, like at the sentence, this sentence here, and this sentence come from this source document. And this source document here, because it is a provenance node, so which means we can model all additional information about this this specific documents, like the file size, author, where's it from. Yeah, you can add more properties on this node. So it kind of balance out at the immediate query level. We know that triple is coming from this evidence here, evidence snippet at this paragraph or even sentence. You can put whatever source that is being extracted here, and then you can branch out to the provenance at this node, because this specific provenance node, this document does not only contain one triple, it contains 1,000 or even more triples, right? So they will be all connected to this node. So yeah, so the reasoning for modeling it this way is normalization. because if we compare the monolithic, like just subject, predicate, object, then you cannot really normalize them. What I mean by normalizing means we are able, we allow this for a multi-hop reasoning question. So for example, because this source document node here, K06, we can do this kind of query. Show me all the facts from the same source document. Why is that powerful? Because this is a powerful proxy for relevance, and also it's a core part of human reasoning, because this subtly allow us to infer that if all the facts are coming from this document, then that means all these facts, they are related to one another. And then on the other end, we have reusability and data centralization. So in the monolithic model, subject, predicate, object, if let's say your source file name changes, let's say it's from K060065 to K070065, then you have to, if you model it in the traditional way, you have to update the source 1,000 times if you have 1,000 facts. But then in this normalized model, you just update the provenance one time. That's it. So it explicitly model that, so we can. This is far more maintainable and scalable. Now, of course, if you do it this way, you can do a lot of auditing query as well. And then, of course, you can also do a lot of graph analytics. Like, for example, show me all the source nodes and rank them by the number of in-degree connections. So in this case, we can address the question of what are my most important sources, and so on and so forth. And also, because we have the temporal aspect being modeled like this, we can also filter out by time which facts are being valid from this time. Let's say I want all facts that are valid from 2025 onwards. This is how you can filter out and all the triples that you can get.
I apologize, just a little technical problem. Could you please repeat the last question you were asked?
Oh, so the last,
or what it was about?
Yes, the last question was on the when we capture this fact here, this triple here. So how do we balance at what level of granularity that we want to capture the provenance? Is it at the sentence, paragraph, and then, or is it at the source document node? So in order to address that, we are capturing actually both at both data point, one at the source level, which is the advanced paragraph sentence level, as well as the originate documents.
Thank you.
Sorry to add, but
Yeah.
it could also be that the traceability could be to another independently developed knowledge graph, correct?
So repeat the question again. The traceability.
It could also be the case that the traceability could be pointing to an independently developed knowledge graph, which is somehow semantically overlapping.
Yeah. So then in that case, we can model the traceability to that specific knowledge graph, right? So because hash traceability doesn't have to be a source document node. It can be anything, because it's a node. You can model it however you want. We can connect it to the other graph as a connector between two graphs in this case. We identify, let's say this fact is coming from two different graphs, then we can specify a connector node that connect both of them.
Yeah. Okay, thanks.
Yeah, I have another question.
Yes.
Here, so it seems like you try to model this with this dynamic singleton property graph, but in the end, do you see any loss of power in terms of the original RDF inference capability, where you gave an example, there are triples are not explicitly presented, but you can infer them because you have that RDF inference built in. So is there any loss of capability here?
So we don't foresee any loss, but rather we add on to the capabilities of the RDF as well. That's the original idea to having a singleton property, because RDF is a basic representation. Even with verification, you explode in the number of sizes. You want it to be able to capture all of them and enhance it. leveraging the also the benefits of property graph. So we are not foreseeing any information loss.
But do you have examples? Do you example or any examples to show that?
Yeah. Let's go back to the. Yeah, right here. So this is what we in our experiment setup. This is what we did. So on the on the left hand side we have the PubChem datasets. Yeah, and this is all the and this on the top is the RDF approach where we have the node and the verified statements like that, and also the object. And then we turn it into a singleton property on the left below, and we are able to run the same queries, although more verbose, but we are able to achieve the same thing.
Right, but does that involve any inference?
No.
Right. So what I want to understand is that, do you have examples to show that this actually enhance the original RDF capability or advantages that you mentioned in this new model, new dynamic singleton property graph? Yeah, maybe you can clarify later. Yeah.
Okay. Yeah, definitely. Yep. And then this way. Okay. So now we have the graph built, and we're gonna use it to augment language model LLM context, for example. So now how do we evaluate this in terms of augmenting the language model context, improving traceability, and reducing hallucination? So in order to address that, we are proposing a KGLM response fidelity score. So basically, this score aggregates the 4 dimensions into one single metric ranging between 0 to 1. 0 as in 0 completely hallucination, to 1 which is non-hallucinated. So we are evaluating set of 4 different dimensions. So in terms of factual correctness, so when we evaluate the language LLM response, is this response, the information contained in this response, is true to the absolute sense. And then the second dimension is the grounding fidelity. So as in, is the information in this language model response directly supported by the evidence retrieved from the reference knowledge graph? And then completeness, does the language model response, does it omit any critical information that was present in the source KG and necessary for a full answer? And then lastly is the extrinsic fabrication. Does this trace back to the provided knowledge graph context? So here are more examples.
Publication status of this?
Still a work in progress. So the first dimension is on factual correctness. The problem here, the problem statement is this information true to an absolute sense? So this is our dynamic SPG. We are modeling the temporal versioning explicitly. So you can see, even though when we have documents where if you want to ask the questions, what are the specs for chemistry 20? It could be ambiguous because are you referring to 20? Which version are you referring to? So with the DSPG, we are explicitly modeling the time as well, and also the source document. So we are able to have the prominence, also the temporal information. So now, specifically, concretely, how do we break down the evaluation? So once we have the language model LLM response, we are breaking down into each concrete statement where we have, for example, if the claim 1 is Model X manufactured by this corporation, we're going to run a query to verify does this fact actually exist in our knowledge graph. If so, yes, it is. It exists, and so on and so forth. So let's say the LLM, total there are 10 different statements. So out of these 10 statements, how many of them can be traced back to the knowledge graph? Let's say it's 8 out of 10. So we have an 80% factual correctness in this case. And of course, this is just one dimension. The second dimension is the grounding fidelity. So basically, the problem statement here is that is the information directly supported by the evidence retrieved from the factual from the knowledge graph. So factual correctness is at the triple level. But grounding is actually referring to the actual source, the paragraph, the sentence itself. Because in our node, we are capturing the relation node, we are capturing the evidence snippet. This triple is extracted from this sentence or paragraph, and then it is connected to this source PDF. So then in evaluating the LLM response, does it trace back to that specific source evidence? So now the transformation on the language model task is it changes the LLM prompt from answering a simple question to more constrained task. Answer the question using only the following facts and cite your answer using the provided evidence snippet. So we want the model to we want the language model to explicitly cite where is the response coming from. And for each citation, we are evaluating on the VET metrics, as in V, valid citation. So when we cite this response, does the link actually work? Did the LLM actually cite the node that actually exists in our graph? If the LLM cites node 99, but node 99 doesn't exist, then that is a hallucination. And then evidence match. At the sentence level or the paragraph level, does the text in the cited source actually support what the LLM said? If the response say, LLM say this device is for adult, but in the cited text it says pediatric use only, then it's a contradiction. And then lastly, the T dimension, which is the time match. So if you evaluate is this cited text valid for the specific time period? Because in medical device, the submission date, everything we have to keep up with that. And also in response to a newer technology, we have to know what are the time range does this specific questions valid from. So if the user asks about 2024, does the LLM cited a fact that expired in 2011? So it's still knowledge. So combining all this VET, if the response fail any one of them, the specific claim scores a 0. So we want absolute match between 1, 2, and all these 3 dimensions. And we calculate how many claims they pass this metric. Then completeness. So the completeness dimension is because when we develop this knowledge graph, we have a reference 510K ontology, and that itself has all these specifications. For example, in 510K, we have the K number, trade name, decision date, predicate device, and so on and so forth. This is just a subset. So when you ask the question about, tell me more about the capnostream 20P from this document K101995, then does the LLM response able to provide all the critical information describing the specific device? So we are comparing the response, the entities, with the reference ontology that we get. So if it is missing some of them, how many of them are being missed? And then lastly, the extrinsic fabrication. Does the answer from the language model introduce new information that cannot be traced back to the provided knowledge graph context? So we have this CPI score where C is cited. So did the model actually provide citation tag? Did they cite any information? Then P, present, is the cited source ID actually present in the knowledge graph? And then internal. So does the information present in the source text? So if the language model sentence has keyword like, oh, this medical device, a subscription costs $50, this specific claim does not really appear in the cited evidence snippet. So it catches kind of the extrinsic hallucination where the model kind of adds the extra and unverified details, which is not what we want. So using that, we'll calculate the score for this as well. And then overall, the fidelity score is actually a geometric mean of all the different dimensions. So lastly, this is the timeline and for the remaining work of this proposal. So from December to February, we'll implement the DSPG on the medical graph and evaluation with the KGLM fidelity score, and then projecting the dissertation defense in next April. And the thesis surrounding this dissertation is data alone is insufficient. There's a clear need of a robust life cycle framework to build and maintain quality, temporal, and attributable knowledge graph. And the impact of this dissertation research will provide a complete framework for creating and managing the knowledge graph lifecycle, a formal model, the SPG, for the dynamic, temporal, and auditable knowledge. Lastly, a quantitative analysis on why and how the knowledge graph can directly impact the different dimensions of the LLM response.
this part is likely to be very attractive if you have decent results. Not that I would like to put more on your plate, but there are many limitations of LLMs, mostly related to the lack of grounding or lack of routing, LLM to the world. And to some extent, you have the implementation of the world model. And those issues involve, the limitations are more than hallucination, more than making of the things. Do you think there are more factors that can be pursued beyond hallucination? The limitations of LLM, and how can you have better solution by KG-LLM architecture?
Mm-hmm. So, I guess to answer that, we will try to go through this evaluation framework and then identify at which specific dimension that the LLM is lacking. Is it because in this approach here, we are actually basically covering different grounds: correctness, grounding, completeness, and fabrication. So then, in order to concretely answer what Dr. said, like LLM, what are the certain limitations? So let's see at which dimension here that the LLM actually suffer from.
Yeah, but see, hallucination only addresses the first item. Completeness or is not necessarily covered by hallucination.
Correct. Because
and so therein lies, given that you have rather comprehensive framework for evaluating KG-LLM, maybe you can, and assuming that you have evaluation on all these factors, I think you might be able to cover. Now, for publication, you may say, okay, I'll just publish hallucination or not. But maybe you can actually cover more of the limitations of LLM, saying, I have developed a KG-LLM approach where the KG and world model provide me the grounding, because of that, I am able to address XYZ limitations of LLM. One of those is hallucination.
Yeah, and also in our title, hallucination is one of them, but improving traceability. Yeah, it's another problem that we want to address. Improving the traceability of the LLMs. Yeah, that is. I mentioned that Dr. Vipo and I were working on a because in the critical domain like medical device, it's very critical. Trace back to where I was.
Just following up on Amit's questions here. The other things where this could have an impact is where it could improve the reasoning capabilities of the LLM. It could improve the planning capabilities of an LLM, right? And the question really is, to what extent are these evaluation metrics possible in a generic manner as opposed to a domain-specific manner? So any thoughts on those?
Yeah, so in this case, we are addressing a domain-specific problem.
Yeah.
But then how can this metric be able to analyze in general domain? I believe we have a lot of different metrics to evaluate that. Like Vipula's work, she's working on the general domain hallucination index, the HVI index, that is addressing the more general question answering rather than the domain-specific ones. And we believe there are existing work that are covering those already.
Actually, I feel that people are the tutorials that they are giving. There's one coming up again that can be improved by not just measuring, but how do you improve with KG-LLM? That's a great opportunity that you have, either by initially adding yourself, adding your work to theirs, or for you to do a follow-on tutorial just focus on KGLL. It's clearly, you can easily cover 90-minute version very quickly with what you have. We'll work on that.
Okay, very good. Let me suggest that we conclude the presentation. I think we're very close to the end.
It's done. Yes,
Done.
So that was
Very
the
good.
slide.
Very good. So we already started really the question part, the more general question part. I would like to ask the members of the audience. There are about 8 of them. There are 8 of them, in fact, in the room, and any non-committee members online to start and ask for the first questions if they have any of them. So we can then move to the committee.
I have a question.
So there is a question from the Hong Liu, and there is a question from the room. I think Hong Liu raised his hand first. So Hong Liu, please go on.
Dr. Liu, hi.
Do you?
Yeah.
Oh, you're a committee member, though. Can you hold on a moment?
Oh, I can hold on. Yeah, I can hold on. If
Question from the audience.
yeah, maybe somebody else can ask.
Yeah, I'm Ranjit. I'm a PhD student here. I wanted to ask the difference between Neo4j and RDF is that you have better graph in traversal for Neo4j, and also the structure. What makes it Neo4j better at graph traverse is the in graph traversals than RDF.
So, see, property graph from Neo4j, that's why the whole reason they are faster is because they have their own proprietary cipher language. The cipher query language, yeah, that is designed to meet their graph structure. That's why queries are very fast, and then you can do all this matching. To answer that, it's because they have their own language.
Okay. Okay. I have one more question. So the difference between knowledge graph and world model, my understanding is that so it's similar to state and action in RL. Like knowledge graph is a environment, and the world model is the action that affects the environment. Or in your definition, I see that world model leads to certain causality.
So this is the
One thing that even during the time of ontology, there are ontology schema and ontology instances, knowledge graph schema and knowledge graph instances, or description and description based. And thus, I'm not sure. I mean, I'm not sure world model represents a new concept, at least the way we define. Because ontology, instance level of ontology representation already been there, always been there. Those were stored in property graph by and large. It can be an idea. So I don't see what exact world model, what actually new world model brings compared to what we already have.
it's okay. This is more in terms of the definition differences. So ontology, think of it as a schema, just a guiding. Like for example,
I know long time ago we built world's first 1 million instance ontology called DVL, what is it called? Something called -DVL. In 2006, we had an ontology, 1 million plus, entities in that. Okay, they basically represent DVL as ontology. Okay, then we created knowledge graphs that had, very large amount. I mean, it's pharma. Let's say pharma, it already has millions of facts. So and those facts are those facts different than what you imply by one model?
one model is an environment that uses the knowledge graph to do whatever you wanted to do. Because one model is a environment representation. In order to get that representation, knowledge graph is the one that is represented.
Okay, so it's just a kind of knowledge graph in the core and the services around knowledge graph. That's all that, right? See, even before one model term is used, we used to build service around knowledge graph. I mean, we have built application in finance using knowledge graph. You remember 2005 paper on the national security example of terrorism and other things. If you remember that, so national security application, and then we had ontology and we had ontology instances, and those were all built. And so that, of course, there were services around that. Anyway, I mean, to keep with the modern usage, it's perfectly good that you have done this. I'm just not sure that is, from a vocabulary perspective, this is probably more recent usage, but I don't see any novelty per se.
Thank you.
I think.
But there is another meaning of word model, if I may jump in. That happened that you can find in logic-based approaches to natural language understanding. So the word model is separate from the grammar and the lexicon, and it is a language-independent description of a domain of the word, if you like.
Yeah, so world model is used in multiple probably contexts, but you should be well aware of the use of world model in a 2000 patent awarded in 2001, which had a very large world model, right? And I use word both ontology and world model in that patent, right?
Yes, yes.
So this was 250 million instance knowledge graph that we had, or you can say comparable. And then that knowledge graph was the fundamental to semantic search, semantic browsing, semantic personalization, semantic advertisement, right? All of those things we did, right? So those are all services built around that knowledge graph, right? So why use 3 and why not use definite, what I did? Anyway, that's no.
Just to add to that, I think in general the idea of world model that is written on the slide is pretty much consistent across different things. So dynamics in general, if I want to map it to what world model means in reinforcement learning and reinforcement learning environment, it's essentially you have a world model that can, given any state, knows what happens once you take an action. That is present in the state. In the patent that you have, the world model meant is how well can you navigate this entire search space, which is modeled in the semantic knowledge, where given any input query, you can map it to a particular term.
So,
from that term,
so are these just two different usage, or they are fundamentally different?
At a high level, they are same.
Okay.
They can be different when you go more deep into it, but at a high level, it's exactly what it is. It is cause and effect. But the cause and effect changes in different contexts.
Sure. But the core definition doesn't change.
Yes.
The definition is the same, but based on the fact that these two are different domains can have different representations that they work with. So that
No, the representation in our case was RDF or property graph. In fact, Tali was implementation was not exactly RDF, but just for the same way Neo4j has chosen, property graph centric thing. Ours was also property graph plus representation and implementation in those days also. And I my first paper in RDF goes back to 2006. No, 1996. Okay. So anyway, I want to make one comment. This is just important for us before we go to the committee.
We also have a question from Dr. Yong Liu, who was very kindly waited.
Sure, let's do that. But,
so Dr. Liu, please go ahead. You're very kind to let the audience here go first.
Yeah, no problem. Maybe just one quick question, and then I can hold on other things later. Yeah, so one quick question is that because your title is proposing a life cycle of knowledge graph, and you mentioned the evaluation, but how do you complete the cycle? Once you have the evaluation results, it's not clear to me how you drive the next iteration of knowledge graph updates or augmentation, because there's a very, very difficult questions in industry is that people are struggling with so-called evaluation-driven development, and applied in this case is how exactly that drives the updates and maintenance. Basically, it's CRUD, right, applied into knowledge graph.
Yeah. So the immediate thoughts that came to my mind is basically evaluating, because the evaluation and we propose here is basically evaluating the language model responses. So what we can do is take a deep dive on what are the chain of thoughts that are being expressed by the language model and the responses, and see what are the limitations and gaps that are there that can drive the second version of knowledge graph that is being used to improve on the second version of the LLM responses. That is about the mind.
Okay.
Following up on this, Joey, what
Yeah.
you've shown here is not a cycle, but you've shown a process, steps 1, 2, 3, 4. So there, you don't show a feedback loop, which would indicate a cycle. So how would you reconcile that?
Oh, the 4 here is going back to 1, 1, 2, 3, 4, and then 4 back to 1.
Right there on the left hand side, there is an arrow back for 4 to 1.
Yeah, there is an arrow, but there is no explanation of the arrow, I think.
Yeah, it's right here. It's being labeled as
And Dr. you are pointing out.
it's being labeled vertically continuous knowledge updates and maintenance.
Right.
I think the
but
concept
I would.
is there. Yeah.
Sorry, I'm stepping on your words. It would be good if you included a statement here.
Okay.
With a detail about what that update and maintenance consists of.
Okay.
It is an example, clear example, I think, as you would need. I don't know whether you would be able to evaluate that continuous cycle for multiple times, but it will be good to do one instance of it.
Okay, I think it may be
Yeah,
time
I have to make one comment before I go.
Oh, yes, please.
So, guys, I think this is potentially a great short-term opportunity to collaborate with Joey on KG LLM or planning and reasoning, aspects. See if you guys can come together and if you can clearly work out how you can do, it would be great because, we take an example of reasoning. We have identified, everybody knows that language model reasoning is very limited, and that even in a knowledge, we have multiple examples of, different kinds of reasoning. And if you guys can figure out, using the same platform, but experiment and show you can do better reasoning because you have access to world model, you might want to do that, or KG, right? And the same thing for planning. If you can figure that out, that would be a pretty good, very timely contribution to the science. If you don't do it, somebody else will do it anyway. A lot of people are doing this. Okay,